Hello and welcome to my presentation on decentralized interledger gateway architectures in authorization scenarios that involve multiple ledgers. My name is Vasilios Siris and I'm with the Mobile Multimedia Lab at the Athens University of Economics and Business. The work that I'll present has been funded by the European Union through Project SOFI, Secure Open Federation for Internet Everywhere. Our motivation is that different types of blockchains have different features. Combining two blockchains for authorization to IoT resources has gains in terms of the lower transaction cost, as we will see. However, the interconnection of the two blockchains requires an interledger gateway, which can be a single point of failure. In order to address this reliability issue, the goal of this work is to present decentralized interledger gateway architectures that differ in their complexity, transaction cost, and ability to handle transactions involving multiple ledgers. Next, I'll discuss the key features of blockchains and how they depend on the blockchain type. First, we have decentralized trust, that is, trust without requiring a single trusted third party. Public ledgers can support a wide-scale decentralized trust, whereas permissioned ledgers support a degree of trust which is determined by their permission set. Next, we have immutability. Immutability is related to the first point, since the majority of nodes need to agree in order to change the state of the blockchain in a trustworthy manner. Depending on the scenario, immutability can also be achieved by other means. Next, we have transparency. Transparency is not only a feature, but a requirement necessary to support decentralized trust. Moreover, there's a trade-off between transparency and privacy, and permissioned blockchains have a higher degree of privacy. And finally, we have availability, which blockchains can support through decentralized storage and decentralized execution of code in smart contracts. Availability can also be achieved in other ways. What is unique with blockchains is that they can support all four features: decentralized trust, immutability, transparency, and availability simultaneously. The scenario that we consider is that of a client that seeks to access an IoT resource which may be disconnected from the internet. An authorization server can handle requests on behalf of the IoT resource. In such a scenario, blockchains can be utilized in different ways. They can handle payments for resource access. They can record hashes of the messages exchanged between the client and the authorization server, and they can execute smart contracts that implement authorization rules. Now consider two approaches that require one blockchain. In the first, the client interacts directly with the authorization server, and the blockchain is used to record only hashes of the messages exchanged between the client and the authorization server, in addition to handling the payments. In the second approach, a smart contract runs on the blockchain. The smart contract handles authorization requests in addition to payments for resource access. As expected, running a smart contract on a public ledger has a transaction cost which is much higher than the transaction cost if only hashes are recorded on the public ledger. Now consider a third approach which involves two blockchains: an authorization ledger that executes the smart contract and a payment ledger which handles the payments. The authorization ledger can be a permissioned blockchain, whereas the payment ledger can be a public blockchain. Observe that combining a permissioned blockchain with a public blockchain, we can achieve a cost which is much lower than the cost if a single public blockchain is utilized. Of course, there are trade-offs, since now the smart contract that executes the authorization logic is executed on a permissioned blockchain. Hence, the trust, transparency, and privacy of the authorization transactions is determined by the permission set of the permissioned ledger. The two blockchains can be interconnected through an Interledger gateway. However, if the Interledger gateway is a single entity, then it can be a single point of failure. To address this reliability issue, our first architecture involves multiple Interledger gateways that belong to the same organization. The Interledger operation now involves all Interledger gateways listening to an event on ledger A that will trigger the Interledger transaction. Next, all ILGs submit the same transaction to ledger B using the same account. Finally, all ILGs listen to an event on ledger B in order to verify that the transaction has been successfully executed. Note that with this approach, all Interledger gateways submit the same transaction using the same account. However, only one transaction will be executed. If ledger B is an Ethereum blockchain, then there's an issue in handling of nonce values. Nonce values are essentially sequence numbers that are necessary for Ethereum transactions. For the same Ethereum account, the nonce values of Ethereum transactions must be continuous with no gaps. This requires a synchronization of nonce values across Interledger gateways since they use the same Ethereum account. This synchronization can be achieved in a centralized manner by the single organization that manages all the Interledger gateways. Observe that this architecture supports reliability through multiple Interledger gateways. However, the Interledger gateways are managed by a single organization. Hence, this architecture does not support decentralization at the organization level. The second decentralized Interledger gateway architecture involves, as the previous, multiple Interledger gateways, which are now managed by multiple organizations. The Interledger operation now involves all Interledger gateways listening to an event on ledger A that will trigger the Interledger transaction. Then one or more Interledger gateways submit a transaction to ledger B using different accounts. This differs from the previous architecture where the Interledger gateways used the same account. Finally, all Interledger gateways listen to an event on ledger B in order to verify the transaction has been successfully executed. As in the previous architecture, multiple Interledger gateways provide reliability. However, the multiple Interledger gateways are managed by different organizations. Hence, this architecture supports decentralization at the organization level as well. Also recall that this architecture utilizes different accounts for the transactions that are submitted by the Interledger gateways to ledger B. Hence, nonce values do not need to be synchronized. However, there's an issue of determining which Interledger gateway submits a transaction to ledger B. This can be important if the Interledger gateways get reimbursed for the Interledger services that they offer. The selection of the Interledger gateway that submits an Interledger transaction on ledger B can be selected based on the hash of the mine block on ledger B. In particular, the selection can be determined by the operation modulo n of the hash of the mine block on ledger B. Such an approach enables the smart contract on ledger B to verify that the correct Interledger gateway actually submitted the transaction on ledger B. The third architecture utilizes a permissioned ledger and in particular Hyperledger Fabric in the Interledger gateway system. Compared to the first two architectures, the Interledger functionality is now split. Level 1 Interledger gateways listen to events on ledger A in order to trigger the Interledger functionality and actions on Hyperledger Fabric. Hyperledger Fabric nodes select the Level 2 Interledger gateway that will submit a transaction to Ledger B. Additionally, Hyperledger Fabric nodes listen to an event on Ledger B in order to verify that the transaction on Ledger B has indeed been executed. It is obvious that this solution is more complex compared to the first two architectures. However, it has some advantages. Specifically, the permissioned ledger in the Interledger gateway system can implement, at a lower cost compared to the public ledger, consensus logic and rules that can consider events from different ledgers. Moreover, the permissioned ledger can reliably and immutably record transactions between different ledgers. Next, I'll present some initial evaluation results on the transaction delay in the presence of errors. The evaluation scenario considers 3 interledger gateways. Moreover, Ledger B is an Ethereum blockchain. The first two architectures have the same performance in terms of the transaction delay, hence the results that I present apply to both architectures. The evaluation scenario that we consider involves generating synthetic interledger gateway errors. When an error occurs for an interledger gateway, then that interledger gateway does not perform the interledger operation, hence another interledger gateway needs to be selected. The results show that, as expected, the interledger delay is higher when the probability of errors is higher. A common criticism of blockchains is that they incur a high transaction cost and high transaction delay. However, this applies only to public blockchains. If public blockchains are combined with private or permissioned ledgers, then we can achieve different trade-offs in terms of cost, trust, and privacy. Moreover, with off-chain transactions, we can have a zero transaction cost, whereas the delay is determined solely by the communication delay. The advantages of blockchains that I mentioned are limited to assets and transactions that reside on the blockchain. Once we traverse the blockchain boundary, we lose these benefits. This is the case of trusting that the IoT resource indeed provides the access that is defined in the authorization. This trust can be provided by utilizing trusted execution environments. Indeed, a device with a trusted execution environment can be seen as a private single-node ledger which can interact with other blockchains supporting decentralized trust through interledger mechanisms. Finally, aside IoT resources, clients can also be constrained devices. Constrained clients can be handled in a similar way as constrained IoT resources, namely utilizing proxies or agents that handle transactions on behalf of the constrained clients. I would like to conclude my presentation with some information about the SOFI project. SOFI is a 3-year project funded by the European Union through the Horizon 2020 framework. The consortium has 10 partners from 4 countries. The goal of SOFI is to investigate the application of blockchain technology to 4 domains: smart energy for electric vehicles, smart meter data, mobile gaming, and the food supply chain. Thank you for your attention, and I'll be happy to receive your questions.